So, in the history of the universe, or at least the College Board, so College Board puts out two versions of the calculus exam, probably all their exams, the US version and then this alternate international version. At some point, they used to publish both versions of the free response questions on their website, and they called the international version the Form B. They don't do that anymore. They save those. They keep them super secret from all the people in the United States. But back in 2002, Form B, I'm pretty sure it was the international version. And take a look at this. This says AB5 and BC5. That means that this was a question that was common to both of the exams. And for you BC students, it was one of the questions that they used to gauge an AB subscore for you. Anyway, let's take a look at what it is. We've got consider the differential equation dy dx is equal to 3 minus x over y. I'm going to stop right there because we haven't talked about solving differential equations just yet. But basically, you can think of, I've just taken the derivative of some sort of implicit equation, and this is the equation that I got as a result. It's supposed to give me the slope of every single point on that implicit equation. All right. And notice that this is a function of both x's and y's, as we've seen in some of those questions. Let y equals f of x be the particular solution to the given differential equation for 1 is less than x, which is less than 5, such that the line y equals negative 2 is tangent to the graph of f. So here's the part of this question that may seem a little bit confusing to us because we haven't heard of this particular solution. So basically what it means is that here I have the derivative. Eventually we're going to learn how to work backwards from this derivative to get the original equation. When I get the original equation, at first it is called a general solution. It's not called a particular solution until I plug in a point that I know is on the original graph. So basically, I've got f of x. Some sort of function, I've taken its derivative and it's given to me right here over this particular interval. And at y is equal to 2, y is equal to 2 is tangent to the graph someplace on that graph. And you can see that it's asking us, first of all, to find the x-coordinate of the point. Why did it switch? The x-coordinate of the point of tangency. So first of all, I've got some sort of weird graph. I have no idea what it looks like, but I know y equals negative 2 is tangent to. That's a horizontal line, right? If it's a horizontal line, let's think about this. We've got some sort of graph, and I have a horizontal line which is tangent to my graph someplace. This is at y equals negative 2. And this is the tangent line. This must be a relative min or max at that point, right? Because it has a horizontal tangent line at that graph. And further, it says find the x-coordinate of the point of tangency and determine whether or not f has a local minimum, maximum, or neither. Well, I think I may have misspoke because it is entirely possible that we have ourselves, let's say, a point of inflection, and the point of inflection could be a horizontal tangent line as well. All right, so that's why it's saying, hey, let's make a determination whether or not f has a local minimum, maximum, or neither one at that particular point. But again, notice it says to justify your answer. Okay, so the first part of this, we need the x value. And we don't have the original function that we would ordinarily stick our y value in to find our x value. So first of all, at the point of tangency and the point on the graph, or I should say on the function, and the line, the tangent line, should share this point of tangency. It has the same xy coordinate on both functions, both the tangent line and f of x. Let's label this thing as f of x, whatever this thing is. So this point of tangency, I know for a fact it has an x value, which I don't know, but its y value has to be negative 2 there because it's a horizontal line and every single y value on that line is going to be negative 2. All right, then. The other thing that I know about this particular line is right here, regardless of whether it's a relative minimum or a maximum point, or if it's a point of inflection, the slope there is 0. The slope of this tangent line is 0, and that's what I'm going to plug into this differential equation here, this derivative equation, in order to find out what my x value is. I have my y value. I'm going to plug that in here, but I'm going to set the whole thing equal to 0 because the slope of that tangent line at that point and the slope of the graph is going to be equal to 0. dy dx will be equal to 0. So there's the first thing that we have to do. We're going to take dy dx, set it equal to 0. That should be equal to 3 minus my x over negative 2. The negative 2 really doesn't matter because I'm going to multiply it over to the other side and make it equal to 0. Multiply both sides by negative 2, it's still 0. It's equal to 3 minus x. And then from algebra, just add the x over x is equal to 3. So there we go. Our point of tangency is 3, comma, negative 2. And I'm probably going to need that thing later. So this was probably worth a point on the original free response question. Okay, so the next thing that I need to do is determine whether or not we have a local or relative maximum, minimum, or neither one. So usually, like, one of the things that we would do for this thing is like we would use the first or the second derivative test, right? And look, I already have myself the first derivative. It kind of almost would make sense that I would just use the first derivative test. I would have to set up some sort of intervals, right? Set up some sort of intervals. Maybe here's the domain that I'm going to use from 1 to 5. But the problem is, what do I do with the fact that I've got both x's and y's here? All of the times that we've used the first derivative test, when we set up intervals, we only had to consider intervals over the x's. But now that we have both x's and y's, it becomes much more complicated. And the first derivative test is no longer a thing that I want to do. This is one of those cases where the second derivative test is the only thing that actually makes sense. I already have the first derivative. I can take the second derivative, dy, or d2y over dx2, in order to perform the second derivative test. All I have to do is put in our critical number, which is what this one is, crit number, into the second derivative and see if it's positive or negative, or, I can't draw some sort of conclusion if it's 0. But that's where I want to start. And it's, like I said, it's the only option that we have for this particular question type. So let's take the second derivative of this. And we'll have to do it implicitly, and it looks like we'll also have to use the quotient rule. So dy dx is equal to 3 minus x over y. Let's take the second derivative of this. So the derivative of the top is just going to be a negative 1, so negative times the bottom, y, minus the top, 3 minus x, times the derivative of the bottom, which I'll just write as y prime, all over the denominator squared, y squared. All right, now ordinarily what we would do is that we would take the first derivative and we would stick it in for where y prime is, right? We've had to do that before in our lessons in implicit differentiation. I'm not going to do that in this particular case, and the reason why I'm not is because I'm about to evaluate the second derivative at this critical number, and I already know what the slope is supposed to be there. The slope there is going to be 0, right? So I'm just going to highlight that this y prime at 3, negative 2 should be equal to 0. Why is it equal to 0? Because that's exactly how we got this, this x value of 3 anyway. Remember this whole entire discussion, it was a horizontal tangent line. So now let's evaluate the second derivative such that x comma y is equal to 3 comma negative 2. All right, my y value is negative 2. Negative 2 is positive 2 minus 3 minus 3 didn't even matter, times 0 also didn't even matter, over my y value. My y value was 2, which I'm squaring. Okay, so all of this stuff is 0, it's going to be gone. I'm left with this 2 on the top and a 4 on the bottom. It's a half. Okay, what does this mean? It means that my second derivative is a half, which is positive. It's a positive number. My function is concave up there, and I have a critical number on that interval. And if I have a concave up, it's going to bend away from, so obviously I did my graph upside down. I didn't know that at the time, of course. And we've got ourselves a relative maximum here. No, we don't. We have a relative minimum. There we go. Now, we got to put the pieces together and actually formally justify this in the same exact way that Jaime Escalante would have expected us to do. So, let's see. I'm going to say that f has a relative, make sure you spell your word properly, minimum at, let's say it is, what was it, 3, -2? And I need to justify this with the second derivative test. And the second derivative test really has 2 parts. You have to first say that the first derivative is equal to 0 there, and then you have to declare that the second derivative is positive, right? Since dy dx such that, I was actually going to write the word such that x comma y is equal to 3, -2 is equal to 0, and d2y dx2 such that the same thing is true, xy equals 3, -2 is greater than 0. And that is it. We have said that the first derivative is equal to 0, which basically declares it as a critical number, and then that the second derivative was greater than 0, which is concave up. It's going to curve away, making ourselves a relative minimum.